Hello, today in this video we will be discussing organohalides very briefly, and before we discuss organohalides we're just going to simply review some of the naming ideals that we have learned about previously, just so we all remember how we're supposed to properly name organic compounds. And here I have a little example that we'll just run through really quick, and if you think you're confident on naming, just go ahead and skip a couple minutes into the video. So remember, the first thing we have to do when we're analyzing a organic molecule is to recognize the parent compound. So it's pretty easy, just this one's very linear. We can easily identify the main chain here, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons long, which means it's going to be undecane. And we also right off the bat see that there is a double bond, so this ending's not actually going to be ane, it's going to be ene. But after we do that, we need to remember which way we want to number this molecule, and because we have substituents on this side off the first or second carbon, and we don't have anything off the first or second carbon on this side, we're going to start numbering from over here. So we're going to name our substituents right under this undecane. And so we see that this is the second carbon, and it has 2 methyl groups coming off of it. So that means we have 2,2-methyl. And then, because this is organohalides, I went ahead and added a halogen in here. Chlorine, so we know that this is going to be a 3. And when we're naming halogens, we add this suffix at the end, oro. So like iodo, chloro, bromo, you just add a O at the end, really. On the 4th carbon, we see we have cyclopropyl. And here at 5, we see that this is where our double bond is, so we'll keep that in mind for later. 6, 7, on number 7, it looks like we have sec-butyl. And then the last one we have here on number 8 is going to be our benzyl group. All right, so now that we have all of our substituents here and we have our parent name, all we have to do is put these together. And remember, we're going to go in alphabetical order. So in this case, it looks like our benzyl is going to be where we're going to want to start off. So let's say 8 benzyl. And then after that, it looks like sec-butyl, since we don't emphasize the sec here, we emphasize the B on butyl. We're going to put that next as 7 sec, that's, and this is undercased, butyl. And after that, it looks like we have some C's, so H comes before Y, so we're going to go with 3 chloro. And then obviously we're going to go right on to 4 cyclopropyl. And then because we have 2 methyls, remember we're going to put here dimethyl. And then some people don't write their ending the same way as I do. I go by the newer IUPAC naming way, so mine's going to be dimethyl undec. And then I'm going to do dash, and we see here that this is on the 1, 2, 3, 4, 5th. So I'm going to do dash 5 dash ene. So it's dimethyl undec 5 dash ene. And that's how we're going to name our organic molecule here. So now that we've kind of reviewed our naming ideals, we're going to move on to just some quick properties over organohalides. And so one of the first properties is that it's a really good solvent. Another property is that it is toxic. So for instance, you don't want anything that has iodine chlorine, bromine. You don't want any of that on your skin. And if you think about it, because of the reactivity of halogens in general, that's why they're toxic. And they can also be used as coolants. So now we're going to go ahead and move on to the synthesis and allylic bromination kind of go together. So we'll talk about those both at the same time. So the synthesis of organohalides is a lot more simpler than the mechanism, which is kind of what allylic bromination is. So with synthesis, really, and I had this up top earlier, it's really just Rx, R being absolutely anything except a hydrogen, and X is the halogen. So I'll write over here, X equals halogen. So to make this Rx molecule, first we need a free radical, and there's only 2 steps. So this is, like I said, very simple to remember what we need to do this. And then the second thing we need, and this could be anything, but for this example, we'll do methane. We need a molecule with a hydrogen to give up. And then we need to react it with a halogen, so we'll go with Cl2. And then we just need this. And we also have this HV, which stands for light energy. So what happens after this is pretty simple. The CH4 is going to give up one of its hydrogens, and the chlorine is going to become a free radical. And then this goes through an additional step, and really all they do is combine to get CH3Cl. And we'll go over how this happens through allylic bromination, which obviously is going to use bromine as its instead of chlorine. All right, let me move this over just a little bit more. So moving on to allylic bromination, we have to understand what an allylic carbon is. And all that an allylic carbon is, that's a 2, is a carbon molecule that is sp3, but is also sitting next to an sp2 molecule. And just remember that when a carbon has 3 bonds, one of them being a double bond, that means that it's going to be sp2. And if it's got all single bonds, that means it's sp3. So in this case, this is our allylic carbon, and that's exactly what we need for allylic bromination. So it works out perfectly. One thing to remember with allylic bromination is the reagent that we use with allylic bromination, which is NBS, which is N-bromosuccinonide. I'll go ahead and write it out here so you guys know how to spell it if it ever comes up. But just remembering NBS is probably going to be good enough if I had to guess. So there we have N-bromosuccinonide. So now we'll go over kind of how this works. So say we have a molecule, and we are going to obviously react it with NBS. And when it reacts with NBS, it also needs heat, and for heat we just write a little delta sign here. So what's going to happen is this is going to react, and the reason I wrote this H here instead of CH3 right here is because this is the H that we're just going to get rid of. And so like I said, we're going to get rid of this hydrogen right here. It could have been any of the hydrogens. We just happened to pick this one. So we're going to have really the same exact molecule. It's just it's going to lose that hydrogen right there. So now we have CH2 here. However, for this to make sense, we're also going to go ahead and add in our HBr to show where that hydrogen went. So what happened for this CH2 to become a CH2 without a double bond here is that, and let me go ahead and change this color so I can show you this, is that this was cleaved in half. One electron stayed with the H and one electron stayed with the carbon. So we have a free electron with this carbon, and that's kind of where the term free radical comes from, because we have this little electron here floating around with this carbon. And that's what's going to allow this reaction to actually happen. So, and then this H, it just attached to the bromine in a reaction that is just covalent in nature. So now we have CH2, CH, and then our CH2 again, but he's got this little free radical. So now what we're going to have to do is really simple, is we're just going to have to react it with a bromine that also has a free radical. And it's pretty easy to guess what's going to happen. It's that the electrons, the free radical electrons from the carbon and the bromine they're just going to combine together to make a bond. So now we have CH2Br, because, and I'll change the color again, because this electron and this electron connected to make a bond. And if I cross out this Br and just put it right here to show you, we can see that the bromine here took place of the hydrogen atom here due to the nature of the free radical electron that's just kind of floating on both the carbon and the bromine in this reaction. So one more thing to briefly go over is going to be resonance, and I put it in quotations because most people don't recognize resonance in this fashion, but the resonance of organohalides. And this is pretty simple if you remember how electrons work with resonance. So say we have CH2, CH, and then CH2 again. And then, and I'll show you where the free radical here is. Let's just say it's like right here. So this is the exact same molecule as CH2, CH, and then double bonded to CH2 here. And we'll put the free radical right here. So we can see that the only thing I did is move the double bond and the free radical here. And the reasons that this is okay is because, once again, I'll show you in a different color. If we watch what this little electron here can do, he can move over here to where a bond would be. And then if we cut this bond in half and put an electron here and an electron here, we can see that this free radical electron can move over here as well. And so we have two radical electrons moving over on both sides, and that's how we get this bond right here. And then this electron would then move just over to the carbon. Like, obviously, how this works is that this bond is with this carbon anyways. The H2 is just kind of, in this visual representation, it's kind of blocking. So I'm just showing it that it's over here. It is with this carbon in this model as well. And that just kind of shows you that this is a quote-unquote resonance structure in which the free radical electrons can just move from bond to bond, and they are equivalent in form and structure in this case. Hope you guys don't have any questions, and I'll see you in the next video.